Thanks, Carl. Okay.
Okay.
It's recording now, yeah.
Okay. Can you hear me well now?
I think so.
Okay. So first, let me say a few words about why I am talking about odd transport. So there are a few interesting things about odd transport. One of them is that it's non-dissipative. So here, odd means it's time reversal. So there's some time reversal breaking in the system. And first of all, it's non-dissipative, so you can have it even if you're at zero temperature, so contrary to dissipative transport like normal viscosity or conductivity. Now, in many cases, it's related to quantum anomalies. So, for instance, in 3+1 dimensions, you have actual anomalies. You can capture this by some terms in an effective atom, like time reversal invariance. And also in 2+1 dimensions, it's related to breaking of discrete symmetries by quantum. Related to this, kind of transfer in topological states is protected. So what this means is you do some small continuous deformation of the system, this integration, when it is protected, the transport will not be affected by this continuous change, as long as you don't change the state. If you're in a gap state and you close the gap, then you can go to a different state and then transfer may change. And related to this, in these condensed matter systems where you have this topological state, in many cases also the odd transport is related to edge modes, to the anomaly flow mechanism. And then these edge modes can carry this kind of transport as well. So there is a lot of interesting physics hidden in this kind of odd transport. I'm going to restrict to some very particular subsets. Okay, so I'm not going to discuss, for instance, anomalous transport in 3+1 dimensions. I think there will be other talks talking about that topic. So we'll restrict to 2+1 dimensions. So that's the Flatland, the title. Now I'm going to talk about gap systems. So this means completely gap, like quantum Hall, or with just few massless degrees of freedom, like in a superfluid, you just have the Boltzmann boson, and everything else is gap. Of course, I will restrict to low temperature, meaning effectively zero temperature. I will talk about clean systems, so no disorder. So in particular, the system will be homogeneous, it will be isotropic, asymmetric as possible. So this will simplify the analysis. And then, of course, I'm going to focus on the breaking of parity and time reversal invariance and what is the effect of this breaking on the transport. So let me start with the odd transport. So just a quick reminder of Onsager relations. So you have invariance under time translation, and you have time reversal invariance. Then you can take a correlator of two operators, let's say two currents or two components of the stress tensor. And then if you do a time reversal transformation, then you change P to minus P. Then you can use time translation invariance to shift the argument by T. And then you end up with the same type of correlator, but now you have changed the current components of the stress tensor component. So this means that if you have time reversal invariance, these correlators are symmetric under the exchange of the two operators. And these are associated to transport coefficients through Kubo formula, so the transport coefficients will be symmetric as well. So this is the content from this point of view of the Onsager relation. Now you break time reversal invariance, then these relations don't have to hold. And this means that there will be some antisymmetric contributions to the correlators or to the transport coefficients. Okay, so you can identify this time reversal of the transport by looking at the antisymmetric components of the transport system. Now, in 2 dimensions, no, we can have a whole conductivity. No? So the conductivity is the coefficient that relates the current to the electric field. And if you have time reversal breaking, then this coefficient will have an antisymmetric part. And if you have isotropy, then the only possibility is that this is proportional to an epsilon tensor. Well, in fact, this is the only antisymmetric tensor you can have. So as you see, because this is proportional to the epsilon tensor, you also need a parity breaking to have a non-zero Hall conductivity. In this case, they come together. Now you can have a similar transport for heat. So this will be the heat current. This is a gradient of the temperature, and the two are related by the thermal conductivity kappa. So again, if we have time reversal of transport, this kappa will be antisymmetric, is proportional to the epsilon tensor. So it will also come with parity breaking. Now for Hall viscosity, there are different ways we can identify the viscosity. Let's use the most intuitive one, which is based on the relation between the stress and the strain rate of a fluid. So here, V will be the velocity of the fluid. This is the strain rate, sigma. And then the stress and the strain rate are related by this tensor of 4 indices, which is the viscosity tensor. So the viscosity tensor, if we have a rotational invariance, has to be symmetric in the first pair of indices and in the last pair of indices. But if we have time reversal breaking, then it can be antisymmetric when we exchange the first pair and the second pair. In the case where the system is isotropic, there is just one possible component that takes this form. So you can, it involves the epsilon tensor and the Kronecker delta. Okay? So it also requires parity breaking. You break rotations, then you can have more components. So you break rotations, but the system is invariant under combined parity and time reversal transformation. There is one more component. And if parity times time reversal is broken, then you have another third component. Now these coefficients are dissipationless. The way you can see this explicitly, you compute an entropy current and compute the divergence of this entropy current. This divergence is proportional to the sources times the fluxes. So it's proportional to the electric field times the current, the gradient of temperature times the heat current, and the strain rate times the stress tensor. Now, because all these coefficients are antisymmetric and proportional to these sources, then everything vanishes algebraically, no? So there's no entropy production. So this is a simple way to see that there is no dissipation. Now, this kind of transport has been observed in experiments, in particular related to quantized transport, at least for conductivity. So for the whole conductivity, this is the very well-known plot of the resistivity, the whole resistivity as a function of the magnetic field. So this line here is the whole conductivity, and these other peaks are the longitudinal conductivity. So you observe that in the whole conductivity you have plateaus. So those correspond to quantized values of the whole conductivity. And then typically at the plateau, the longitudinal conductivity is zero because the system is flat. You can characterize the conductivity in this way. So there is this factor here, which is, you want a quantum unit of conductance. And then there is the factor in front, which can be an integer or a fractional number in this quantized system. So this number mu is known as the filling fraction because it tells you the relation between the number of particles m to the amount of magnetic flux in some quantized units. If the system is completely homogeneous, so if the density and the magnetic field are uniform, then mu is simply the density of particles divided by the magnetic field. Okay, so in these quantum systems, mu is quantized. And this was first observed in the 80s for the integer effect. It became a Nobel Prize, and then the fractional quantum Hall effect was observed a couple of years later. And then, together with the theoretical explanation by Lappin, it was also given another Nobel Prize. Okay. And if you want, this is the starting point of all these topological states in condensed matter, because this filling fraction is protected in the sense that small deformations of this system in the quantum Hall state doesn't change. This new has to change by it has to have discrete jumps. It has to change to another fractional number or to an integer. Now, another transport coefficient, which is also quantized, is the thermal conductivity in this quantum Hall system. Now, this was the value of this thermal conductivity was given by these figures in green in terms of this coefficient C, which I will talk a little bit later. And this quantity here that you want is the quantum unit of thermal conductivity. So there are several experiments trying to measure this thermal conductivity. I took this plot from this one here, the one that is underlined. And what you see here is that they measure experimentally the amount of heat transferred by the system, depending on the temperature, or rather the temperature gradient. And then they observe that they can explain these curves if the thermal conductivity is proportional to this quantum unit times more or less 2.5. So this means that this C is more or less 5/2. So this is a fractional number that was predicted by theory. Okay, it's quite an interesting result because this half fraction is related to having what are called Majorana modes in the bulk. Okay, so this means that the state that describes this thermal conductivity is quite special. It's supposed to have some non-abelian statistics. In principle, this kind of non-abelian statistics can be used, for instance, for quantum computing. Okay, so this is the experimental observation of this kind of quantized transport in the thermal conductivity. Now, for the Hall viscosity, there is no similar result. Okay, the fact that you can have a quantized Hall viscosity was first predicted by Aaron, Seiler, and Onsager in the 90s. You could try to measure using homogeneous electric potentials, and there are more concrete proposals that other people like De La Crepas and Gromov have proposed, but there is no measurement of this Hall viscosity. This quantum Hall system were just expected to be quantized. Now, there are other measurements of Hall viscosity in systems where you can approximate the motion of the electrons by some effective hydrodynamics, and then you can predict the effect of the Hall viscosity on the transport of charge, for instance. And this is a plot of the measurement of this Hall viscosity in graphene for different temperature. Okay, so in this case, you have a non-zero magnetic field. That's the thing that is producing the Hall viscosity. You see that the Hall viscosity goes to zero at zero magnetic field, and then it increases with the magnetic field. it has also been measured in other kind of systems, like this colloidal fluid. Yes, so this transport coefficient has been observed, but not the quantized version. So this will be something that is very interesting to see in the future. Okay, so how do we measure this kind of transport? Well, or how we describe it using some effective field theory method. So the effective field theory, this approach we will restrict just to low energy degrees of freedom to describe the system. Then we will couple the system to some background sources, and then we will use Kubo formula to derive the transport coefficients by using this coupling to the background sources and see what is the response to the background sources. Now, in the effective theory, we will do a systematic derivative expansion. So we will assume that all the fields vary very slowly in time and in the space, and then use that to make the systematic construction of the effective theory. And then we will use symmetries to constrain what are the possible terms that we can have in the effective theory construction. Okay, so our goal is to describe this odd transport using this effective theory. So as an example of what I mean by this, let's look at the Hall conductivity. This is very well known, but let's just go over it to have an idea how this works. So we have, let's say, charged fermions coupled to some background gauge field, and then there is a magnetic field that will be large and non-zero. So we can assume that fermions will be in the Landau levels. So we will assume that will be some completely Landau levels, or we will be just in a fractional quantum Hall or integer quantum Hall. And we can also have an external electric field. Now, with this assumption, the system is completely gapped. The gap is proportional to the magnetic field. And then if we integrate out all the dynamical degrees of freedom, we will just have a generating function that depends on the source. Okay? So no dynamical degrees of freedom in the low energy effective theory, just a generating function. To lead in order, as you know very well, this is just the Chern-Simons term. The filling fraction appears here in front of this position. And then this generating function can be corrected by higher order derivatives that depend on the electric field, derivatives of the magnetic field. So we can compute the response to the external gauge field by taking variations of the generating function with respect to the background source. For instance, the current will be the variation with respect to the gauge field. And the Chern-Simons time will give a contribution like this one. So if we look to the time component of the current, which is the density, just is the filling fraction times the magnetic field. So this recovers the relation I showed you before. And then if we compute the space component of the current, then we see that there is a Hall conductivity. We have the epsilon times the time, the electric field. And again, the Hall conductivity is fixed by the filling fraction. Okay, so this generating function, this Chern-Simons action, it covers the expected result for the transport. Now, how do we get thermal conductivity and viscosity? We can proceed in a similar way. So for this, we need background sources that couple to the stress tensor and to the energy or the heat current. The thermal conductivity will be related to the heat current, and the viscosity will be related to the stress tensor. To define the response that give us these transport coefficients, we need sources that couple to these operators. Now, the stress is produced by geometric deformation, so we can just couple spatial metrics to the stress component. And then the energy current should be sourced by some kind of vector. In principle, it's a vector that couples to the Hamiltonian, so it's a vector that couples to the time derivative. So you can generalize it by a coupling of the derivatives to the vector. Now I'm going to focus on these geometric deformations. It's very interesting also to look at what happens with energy current. So this is what leads to all the Newton-Cartan formalism. That also gives very interesting results. But that's a bit more technical. So this is a much simpler discussion to discuss what happens with the space part of the metric. So we'll focus on this for this time. So let's talk about this geometry and the relation to this transfer. So imagine we start with some non-relativistic Fermi. We can couple to the space metric in this way. So we simply introduce a volume factor, the root of the determinant of the metric, and we couple the kinetic term to the metric in this way. No? And of course, these derivatives will be covariant derivatives where the fermion is coupled to the gauge field. Now, if you set all the sources to 0, this will be just the action, the usual action for a non-relativistic fermion. Okay, so in principle, you can add more terms here, like potential terms for the fermion interaction among the fermions. Now, this is invariant under some local symmetries that involve transformations of this gauge field and the metric. So if you want, this is some kind of a spurious transformation that you have when you introduce this background field. So first of all, you can do a gauge transformation that will shift the fermion by a phase. So if you have an infinitesimal gauge transformation, you just multiply by an imaginary factor. And then, in order to be invariant, you have to shift the gauge field by a gauge transformation. So the derivative of the parameter alpha. Now, in addition, you have another not so trivial transformation, which is some non-relativistic deformations that was first introduced by Conan Gates to describe superfluids. Now, under this transformation, the fermion transforms as a scalar, the metric as a tensor of rank 2. The time component of the gauge field transforms as a vector, as the time component of a vector. But the space component of the gauge field, apart from the normal transformation, has an additional contribution in order to make this invariant. So this is the extra term in red that is proportional to the mass, and this is proportional to the time derivative of the parameter of the deformation. Now, you can, there is a global symmetry even in here, which is if you choose the gauge parameter in this way and the deformative in this way, then actually the gauge field doesn't change. So this is just a global transformation of this action. Okay, and that's precisely a Galilean transformation. Okay, so if you have a system which is both invariant under this gauge transformation and invariant under this non-relativistic deformative, automatically going to be Galilean invariant. Okay, and this is something we're going to impose in the following. Now, how is related the whole viscosity to the geometry? Okay, so what is the response we want to see to measure the whole viscosity? So first, consider a non-relativistic fluid. We can write the forward velocity in this way, so the time component will be just 1, and the space component will be the velocity of the non-relativistic fluid. And you could have this if you start with a relativistic forward velocity and expand when the speed of light is very large. Now, if we couple the metric to a fluid, then in order to have a covariant strain rate tensor, we have to change the derivatives by covariant derivatives, like here. When you expand these covariant derivatives, you just have the normal strain rate tensor plus this other component. Okay, so so they depend on the Christoffel symbols of the metric. Now, if the metric is just trivial, except for the space part, where we introduce time-dependent part for the space components of the metric, and we set the velocity of the fluid to 0, then the strain rate tensor is non-zero, but it's proportional to the time derivative of this perturbation of the metric. So this means that the stress in the presence of this fluctuating metric will have a contribution proportional to the Hall viscosity, which is proportional to the time derivative of the space components of the metric and has this epsilon factor. Okay? So this is the kind of response we will see when we have this non-trivial geometry. Okay? This is the thing we want to obtain from the effective action. Now, if we start with the original system, which was involving these fermions and was invariant under these transformations, these gauge transformations, then when we integrate out the fermions, the resulting effective action or the functional should be also invariant under the same transformation. And we know if we have in quantum Hall, we will have a 10 Simons term. However, because as I showed you, the space component of the gauge field doesn't transform in a convariant way, the 10 Simons is not invariant under non-relativistic deformations. So we need to add something to this action to make it invariant. Okay, this is what Son and I did back in the day. It turns out that the term you need to add is like this term here. It involves the electric field square and is coupled by the magnetic field. Okay, so this is this term will be there in a derivative expansion, but now the coefficient is fixed by requiring this invariance. Now, this has a very natural physical interpretation. If we take a variation with respect to the gauge, with the vector gauge field, we take two variations that will give us the current correlator. And this will have an omega or a frequency square term contribution, which gives a term to the conductivity, which is linear in the frequency. So this contribution, which is linear in the frequency, and you can see here that this is giving a contribution to the longitudinal conductivity because there is just the metric here, not the epsilon tensor. So this contribution to the longitudinal conductivity should be present there in a Galilean invariant system, because when we have a Galilean invariant system, there will be a contribution of the longitudinal conductivity, which will take this form. It's linear in the frequencies. There is this pole that is related to the center of mass motion of the system, which is protected if you have a Galilean invariant system. And this term captures the first correction. No? So when this omega squared in the denominator can be put to 0. Okay, so that's one example of an application of this type of construction to the effective. Now, to discuss the Hall viscosity, I need to introduce a few more formulas related to the geometry. So I'm going to introduce this strain field, I call it Wielbein, or people call Wielbein. And you can think of them in some way as the square root of the metric. Okay, so these Wielbeins have two indices. One index is just a space index, and the other index, you can think of it as an index in a frame where you choose a basis of vector which is orthogonal. Now this is a 2 by 2 matrix which will have an inverse. So you multiply the Wielbein by the inverse Wielbein, you just get the identity. this will have 4 independent components, while the metric, which is symmetric, only has 3 independent components. So the extra degree of freedom is removed by a new gauge symmetry that corresponds to rotating the internal index by a space rotation in the orthogonal plane. Now, to this new gauge symmetry, you can associate a gauge field, which is the spin connection, and you can write it in terms of the wavelengths and the covariant derivative in this way. Now, in principle, once you have the spin connection in an arbitrary system, you can have quasi-particles where there is a non-trivial coupling to the spin connection. So electrons don't couple directly into the spin connection. They just couple to the matrix, like in the previous action. But if the effective theory has a quasi-particle description, these quasi-particles carry some kind of angular momentum, then they can couple to the spin connection. Okay, so you can have that the covariant derivative gets an additional contribution. Now, we can use the spin connection to construct the effective action that will give us the Hall viscosity. This is called the 1C10. Was introduced in 1992, but not to discuss Hall viscosity directly, but to discuss the properties of the quantum Hall state in non-trivial geometry. Okay, so it looks like a Chern Simons where you couple the gauge field to the spin connection, and the coefficient should be proportional to the field infraction times a new factor which I call smaller. Okay, in particular, inside this term, you have a contribution which is proportional to the magnetic field times the time component of the spin connection. So you now do a small perturbation of the VL line, or a small metric perturbation. Then you'll have a contribution coming from this time component of the spin connection to this 1C10, which is proportional to the magnetic field times a term like this. So it's quadratic in the fluctuation. Now, if you take a variation of the 1C10 with respect to the metric, you will find that this precisely gives a contribution of the form we write this before. We have written before. Okay, and this coefficient that appears here is just proportional to the Hall viscosity of the system. Now, this parameter S can be interpreted in the following way. So this is the original discussion about this thing by Wen and C. So inside the 1C10, you have a contribution which is the time component of the gauge field times the curvature of the space curvature. Okay, so when you integrate over a space, that will give you, this is a topological invariant, which is the Euler characteristic. Okay, so you have a contribution which is proportional to the Euler characteristic of the two-dimensional space, and then a contribution proportional to AT. Okay, so this is a shift of the charge of the system. So this means that the total number of particles is related to the magnetic flux by the field infraction, but also shifted by the field infraction times this big S, which is 2 times smaller. Okay, big S is 2 times smaller, and this is now in this paper we showed that in the quantum Hall system, the Hall viscosity is proportional to the shift over 4 times the density. Okay, so this justifies this identification of a small f with B. Now, this number is quantized in the integer quantum Hall system. The shift is just proportional to the field infraction, which is an integer. In a Flatland state, the field infraction is 1 over an odd number, and the shift will be just this odd number. Okay? And in other fractional quantum Hall states, this shift is also quantized. So this means that the Hall viscosity over the density is quantized in this system. but there is no topological invariance associated to this. Okay, so in the case of quantum Hall, there is a topological invariance. Here, there is no topological invariance. And this is shown in the fact that there are no edge states associated to this, to the one system. Okay, so we do a gauge variation. In principle, the one system will change by a boundary action, but by a boundary contribution. But you can compensate that by adding a term which is local at the boundary. Okay? For the Chern-Simons, you cannot do that. You need to have edge state for the usual Chern-Simons. But for the Wincy, you don't. Okay, so this is a case where you have quantization, but no, not really topological. Now, again, it happens that this one system is not invariant under non-relativistic deformations. So we need to add more terms to make it invariant. In this case, we have to add looks like this. And this gives a contribution to the whole conductivity, which is proportional to the space momentum square. Okay? So this means that there is a correction to the whole conductivity proportional to the whole viscosity. You could use this to measure the whole viscosity. But there are also other contributions to the whole conductivity of the same type. So it's not a direct measurement. You need to measure other things as well. Now, this relation you get from the effective action, you can also get applying Galilean invariance to Kubo formulas directly. So it confirms the microscopic calculus. Now, for the thermal Hall conductivity in quantum Hall, you can describe it by adding a topological term of this type. So this will be like Christoffel symbols, I think one form, Christoffel symbols. So this is a gravitational Chern-Simons term, and this coefficient is a topological invariant, and it's related to the central charge of edge states at the boundary. Okay. So, contrary to the whole viscosity, this is related to the topology of the state. Now, the gravitational Chern-Simons can also give a contribution to the whole viscosity. Okay. So this is something we show. Okay, let me say a few words about chiral superfluids now. The chiral superfluids, now in 2 dimensions, we think about fermionic superfluids restricted to some thin 2-dimensional layers. So there are some Cooper pairs, but they are in a state that has non-zero orbital angular momentum transferred to this plane. Then in experiments, it has been observed in the A phase of superfluid helium-3, and there are some proposals called atoms. Also, this state is related to some chiral superconductors. Now, the more microscopic description will be having some kind of PDG Hamiltonian, where the order parameter has a vector index. And then you can couple this to geometry in this way. So you couple the kinetic time of the fermions in the usual way to the metric. And you couple this vector order parameter to the VLY. Okay, so now this range index is associated to the direction where the vector parameter is pointing. Now, when this is non-zero, there is a breaking of spontaneous breaking of symmetry. So there is the U1 particle number that rotates the phase of this fermion, and you can write it as an SO2 rotation as well. And then it combines with the SO2 rotation of the frame field into some kind of diagonal SO2. Okay, so this parameter breaks the U1 particle number and this rotations to a diagonal SO2. For the chiral superfluid, you just make the X and the Y components proportional to each other with an I factor. Okay, so this will be Tx plus I Ty. Now, To construct the effective action, you will integrate all the fermions and also the massive modes of the order parameter. You will have an effective action that depends on the background sources and also on the phase of the order parameter, which is the Goldstone. And this massless. And now the generating function will be gauge invariant, but you require that the covariant derivative of the Goldstone involves also the spin connection. No? Because if we do rotation of the frame fields, then this order parameter will rotate. So this means the phase will shift by this isotropy rotation. So the spin connection will be here. Now, to construct something which is invariant or covariant under the geometry, you need to take this combination of covariant derivatives. And then you need to add also this term, proportional to the magnetic field. So this term appears because here you have the time component of the spin connection, and that is not transforming in a covariant weight. So you need to compensate with this magnetic field. Now the effective action will be just an arbitrary function of this scalar x. And then to actually find how the Goldstone boson behaves, then you need to expand around non-zero density state, which means this theta has a leading contribution, which is chemical potential times time, and then there is the fluctuation phi. And then we assume that the derivatives of the fluctuation are much smaller than the chemical potential. So if you expand this action, you will have several contributions that are higher order in derivatives, and this is expansion. This is essentially the kinetic part of the Goldstone with the speed of sound. And then you see there is this term with single covariant derivative, which will be important because it contains the time component of the spin connection. And here, among other things, you see there is a cross term that involves the time component of the gauge field and the magnetic field. So this is like an incomplete Chern-Simons. This gives some of the properties of the quantum Hall system, like density related to magnetic field, but it doesn't give a Hall conductivity. Okay, and this is something that was discussed also in the context of anionic superfluids, with Polyster and Wilczek. Okay, so from this effective action, if one studies the response to the external sources, we can abstract the Hall conductivity. It has this form, so it's proportional to this S, the coupling to the spin connection. And then, of course, there is a pole corresponding to the Goldstone, but you see that at zero momentum, the Hall conductivity vanishes because, as I said, we don't have a complete Chern-Simons. But there is some Hall transport at non-zero momentum. Now, the thermal Hall conductivity can have a topological contribution from a gravitational Chern-Simons. This only happens in the DCS phase. So this means when the system is with each other. And then in that case, you'll have this Majoranite mode. Now, the Hall viscosity is non-zero, and this comes from this term I was telling you about before, that has a single covariant derivative. You have then a term which is proportional to the density times the time component of the spin connection. And this is very similar to what we had in the Wensi term, just replacing the magnetic field by this density. Okay, so this gives Hall viscosity, which is proportional to the density times this small s, which you can understand as the orbital angular momentum per particle. Okay, so this is based on the result by Reed. Okay, so we recover the right behavior from the effective. Okay.
Can I ask a question?
Yeah.
So in your paper with Son, you showed quite generally that the Hall viscosity would give a k-squared, a momentum squared correction to the Hall conductivity. Do you see this correction too? Because here your Hall conductivity is already k-squared.
Well, no, it's a different system. So that was only for quantum Hall. So there you have to add this term, which is like the electric field square, right, to the Chern-Simons term. But here you don't have this Chern-Simons term. You have this contribution, which is like an incomplete Chern-Simons. But this term by itself is already, or if you want, this capital X by itself is already Galilean invariant. And as you see, that doesn't involve the electric field. Yes, so here, the contribution you had in that case doesn't appear here.
Okay, thank you.
Any more questions? Okay. So that more or less summarizes the results for this system. Let me briefly go over Hall viscosity in some other systems, or Hall transport in some other systems. First, in the relativistic case, you can also find a Hall viscosity. So the Wendt term, you cannot use it in a relativistic system because if you have a Lorentz invariance, then the spin connection cannot be written as just an abelian gauge field. It will be some kind of non-abelian gauge field. So then you cannot combine it with the gauge field to make some covariant action. But you can do something else, which is what Robertson did, and is to couple the gauge field to a conserved current that they call the Euler current. And it has this more or less complicated form, but it involves the curvatures here. And it involves this U, which is essentially proportional to the magnetic field, the time component is proportional to the magnetic field, and the space component is like the Hall current. Okay, so this kind of coupling gives rise to a Hall viscosity in the relativistic system. If you take the non-relativistic limit of this effective action, then you recover the Wendt term. Okay, so this is another explicit way of writing the Hall viscosity, where you see that it is really not a topological term. Okay? You see that this current involves two epsilon tensors, it's not related to topological contribution. Now, because this is hollow matter, let me say a few things about holography. So Hall transport in holography was first discussed, I think, by Harmon and Hopkins. So you have a magnetic field in some 2+1 system where you can, it's a strongly coupled and you can describe using holography, then you find there is a non-zero Hall conductivity. You can also have an anomalous Hall conductivity. So in the absence of magnetic fields, if you have a term in the bulk, so this will be D for X. You should have a term in the bulk which is F with F coupling to some scalar, or even this will be a constant. So it will be an anomalous Hall conductivity in the duality theory. You can have a Hall viscosity if you have some kind of scalar coupled to an R-wedge R-term. Okay, but if this is constant, there is no Hall viscosity. So here you really need some kind of non-trivial state, like a superfluid. If you have a magnetic field, the Hall viscosity vanishes. So this is different from what you find in this quantum Hall system. But you can also have a Hall viscosity in some kind of p-wedge superfluid. So in that case, you have non-abelian gauge field, and then you impose some kind of locking between the gauge symmetry and the space rotation. So this will be an SU2 gauge field, and then you take the two components of the SU2 and lock with the two space components. So this introduces parity breaking through the structure constants of SU2 with epsilon tensor. And finally, you can also have a whole viscosity for non-zero magnetic field. So this is something we did. But for this, you need to add a higher derivative term. Okay, so the kind of higher derivative terms, we can add a curvature terms coupled to the gauge fields that produce the magnetic field. Okay, so this kind of action in the gravity buoy, you can think of it as coming or as being related to this Euler current construction. Okay, if you remove one derivative from here, then you have the gauge potential coupled to the curvature and coupled to the electromagnetic field, which is the kind of structure you have in the Euler current. Okay, so this is more or less how you can have a whole transport in this holographic model. Now, in all these cases, except maybe in this one, you have that the system is not capped. So these are compressible states, and the transfer coefficients are typically not quantized. Okay, only in some anomalous cold conductivity examples you can have that this whole transport is quantized. Okay, so I think, yeah, there is no much time left, so let me go over this quickly about duality. So the idea of this dualities is to write the effective action in a different language. I was using this Boltzmann button, and I was just writing the idea functional for quantum Hall. You can unify the superfluid effective action and the quantum Hall effective action by using this particle-vortex duality. Okay, and then you can write effective actions that are more general. Actually, they become easier to write in this language with the Boltzmann. So the idea is in 2+1 dimensions, you can take a conserved current and dualize it in terms of some statistical dynamical gauge field. So the current will be the dual of the field strength, and then by the rank identity, the variance of which is 0. Now this means that the time component of the current, which is the charge density, is equal to the magnetic field of the statistical gauge field. And also it means that the divergence of this electric field is equal to the vorticity of the current. Okay, so you have vortices in this 2+1 system. They will act as sources of the electric field, okay? So as particles of the electric for the new field. Now the usual coupling of the background sources, the gauge field at the spin connection to the current, becomes some consignment will decouple the background sources to the statistical gauge field. As usual, we have to construct an effective action which is invariant. Then, depending of the system we have, there are two options. The first option is that everything is gapped, like in the quantum Hall. This means that we should add a consignment for the statistical gauge field, like this one here. And then if we integrate out the consignment, which is just, this is a Gaussian action, so it's completely trivial, then you recover the effective action we were writing for quantum Hall. Okay, so you recognize the consignment for the gauge field. You have a mixed term, which is a Wensi term, and there is an additional term that should be there as well. Now, you can generalize this construction by having several of these gauge fields. Then this coupling can be a matrix, and here you can have a coupling of these gauge fields with different charges to the two background fields. Okay, and that will describe a whole family of topological cases related to the Flatland and quantum Hall, and also to chiral superconductors. Now, in chiral superfluids, there is no mass gap. Now, notice because this gauge field is in 2+1 dimensions, there is only 1 degree of freedom, and that degree of freedom is the dual version of the Gaussian boson. Okay, so we shouldn't gap it. So this means that there is no Chern-Simons term. Okay, and this means that the whole conductivity will be zero in this system. So you can see it directly in this language. Now, if we have a background density, this means the magnetic field for the statistical gauge field is non-zero. So this mixed Chern-Simons will give a contribution which is proportional to the spin connection. Yeah. And in this way, we recover this language, the contribution to the whole viscosity. Now, the thermal Hall conductivity will come again from the gravitational Chern-Simons. So, it's not directly related to the statistical gauge field. Okay, so let me finish by mentioning a few other things. So we also look at topological defects that were induced by curvature in the P-wave superfluid. So for instance, if you put it on a sphere, the state cannot be homogeneous. You should have either some vortices or maybe rather vortex anti-vortex or some domain wall. You can explore this kind of odd transport in rotating bosonic superfluid. In that case, the superfluid itself doesn't break down reversal invariance, but when you rotate, the vorticity introduces a breaking. So you can have a vortex lattice, and then you observe some Hall transport. But for instance, the Hall viscosity, at least in the mean field approximation, will be zero. Then there is some recent work where Ambry and Felix studied the Chiral superconductors that has the effect of gapping the Goldstein, and also that changes the whole transport. And you can generalize this kind of dual construction in terms of the particle-vortex duality to other kind of systems, more exotic, which are these fractons. So this was studied, for instance, by these people. So fractons, you can describe them using gauge fields that have more than one index, if you want. So they can have 2 indices or more, and you can associate to them not just conserved charges, but also dipole conserved charges and so on. That introduces some kind of funny kind of transport. So this is a very interesting topic that is being quite hot now. Okay, that's all I have to say. Thank you.
Thank you very much. We have questions, please. So anyone who wants to ask a question, just unmute his mic and ask, please. Or if he's having problems, he can write it on the chat, he or she.
Yeah, probably. Can you?
Yeah, we can hear you, Carl.
Okay, great. Yeah, I have a question, and let me see. Most of the time in your talk, you talked about gapped systems, right?
Mm-hmm. Yeah.
But then the action you wrote down for the fermions was a non-relativistic fermion action.
Yes. So,
but a non-relativistic fermion is always ungapped, right?
Well, if you have a magnetic field, it's gapped. So if you have a strong magnetic field and you are in a field lambda level, then it's totally gapped. So
it's okay.
And then in the superfluid, it's actually gapped because you have this cut into the order parameter.
Okay.
Carlos, is this the reason that some of your effective actions are singular when you take the magnetic field to 0?
Yes, so in the generating functional, you assume that there is a gap and then you do the expansion in derivatives over the magnetic field. So if you take the magnetic field to 0, your approximation breaks down at the effective action. Doesn't make sense.
Thank you.
No more questions for Carlos. I'm not seeing anybody speaking or writing. Okay, then let's thank Carlos again. There's no clapping, but we thank you especially for your patience with the yeah, there is like reactions for the yeah. Let me say sorry to everybody for the logistic troubles, and let me also say that we have 2 talks next week. So next talk will be by Jan Sanen on Wednesday. And we also have that will be at the same time as today. So it's like 5 Central European time. And then we also have a talk on Friday at, so this is for Europeans and Asians because it's at 10 in Europe. And you by Lily, and you have the info on the web that I just wrote here on the chat, but you can also probably get in many sources. So if there's no more questions, we will end here, and thanks Carlos again and everybody for attending.
Okay, thank you.
Thanks Carlos, and thanks everybody. Bye.
Yeah.